to the cloud. But don't worry, I'm gonna cut this and upload the one from last semester that I have. All right, so let's get back here. So here, when we are gonna assign loads in X direction and loads in Y direction. Let me double check it's recording. Okay, yeah, it's recording. So in this one is going to ask you, what is the direction of the earthquake that you want to assign to your building? Is it an X direction or a Y direction? And usually when we design earthquakes, we assume that there is some accidental eccentricity in the building. Why? If this is my slab, and I did some modeling, and I get the center of mass of the slab, but I didn't include the stairs, and I didn't include many things inside the building that can cause some accidental eccentricity. Because usually when an earthquake is hitting a building, so we usually put the forces at the center of mass. But the location of the center of mass is not as perfect as the real life is. So we usually assume what is called accidental eccentricity. It is equal to 0.05 of the length that the earthquake is hitting from. But we are not gonna get in this debate. We are gonna only care about the X direction and Y direction. But in actual design of building, we need to include accidental eccentricity. So I'm gonna uncheck this, all of these, and I only include earthquake in X direction. Okay, so I put an earthquake in X direction, and then it's gonna ask you, how do you want the software to calculate the fundamental period of the structure? So there is a table in the code that tells you based on the structure physical parameters, like if it's has a shear walls, if it's a frames, if it's a steel, whatever the structure is. This one, here, this table, and it tells you how to calculate the fundamental period of the structure. It multiply a factor by the height to the power x. Based on the height of the structure, multiplied by some factors, you can get the fundamental period. And actually looking at all of these, moment resisting frame was lots of information. So we are gonna pick all other structures, which is 0.02 for CT, the factor, and the X is 0.75. Based on these two numbers, I will go back to ETABS and you choose what numbers that you are gonna pick. So I'm gonna pick 0.02 and 0.75. These are the parameters that you will use the height of the building that you have. So the CT is 0.05, and then you multiply by the height to the power X. I believe 0.02 multiplied by height to the power 0.75. You can, this is program calculated, so that's the program is going to calculate it for you. Or if you want to calculate it, approximate, and you put the number here, that's fine, okay? But I already choose it here. And the second thing, it asks you about some information. What is the story range? So it asks you, where do you want to put the seismic load? Do you want to put the seismic load started from the bottom story to the top story, or you want to put the seismic load at somewhere else? Usually the seismic load is coming from the ground. So it is from the base to story number 60. Then this one is gonna ask you for the seismic parameter, and it has method 1 and method 2. So let's see what is method 1. So method 2, it asks you about all the parameters of the earthquake. Like ask you about what is the spectral acceleration, SDL, SD1, the one that we have from the website. But you tell me, but we already included this when we defined the responsive spectrum. Why we are doing it again? So if you use method 2, it doesn't care about what you define for the responsive spectrum. But if you use method 1, it will take all the information that you provided for the responsive spectrum. So if I click on method 1, it will ask you, where is the responsive spectrum that you want me to get the parameters from? And we just defined a one is called function 1. Actually, we didn't name it. Let me double check. Let me save this one. I said, okay. Okay. Define functions, responsive spectrum. Oh yeah, we didn't name it. We can modify it so that we can know that function 1 is ASC 722. And let me say, okay. And when we go back to define load pattern, earthquake X modify. So when I say method 1, I can choose ASC 22. You can choose function 1, but this makes much more organized. So once you click, it's already take the numbers that you already put in your model, and it asks you about some other information, but you can keep it as is because it's already used all the information that you gave from last step. The last part that you need to define is the factors. It's gonna ask you, what is the response modification factor R? We talked about response modification R to reduce the forces, but how the software is gonna reduce the forces, it needs some information. So that we need to go to the code to get them. Based on the structural system, is it shear walls, is it frames, is it steel frames, is it reinforced concrete frame, and it gives you all this information. So there is a table in the code here. I'm gonna provide you this presentation so you don't look like you can get these numbers easily. So all the boxes that it's in red, this is what we are gonna use. For example, here, I'm not sure if you can see or not. I'm gonna have a special reinforced concrete shear walls because we have shear walls. It gives you what is the value of R. It gives you what something is called overstrength factor. It gives you the deflection amplification factor. So you will use all these parameters and input them in the ETABS model. So usually 5, 2.5, and 5. So I'll go back to ETABS here. And I put all these parameters like R is 5. Occupancy, the importance factor is 1. The one that I put here, based on the risk category. System overstrength factor was 2.5. And the deflection amplification factor was 5. So I'm done with the earthquake in X direction. If you want to put another one in Y direction, you will do the same thing. Add a new load, sorry. You will add a new load like Y, and then seismic, ACE 722, and then add new load, and then modify, and keep input all the parameters. But rather than having earthquake in X direction, you will have it in Y direction, and then you will say, okay, after changing all the parameters. And this one, you will make it message 2, you see, and then you change this one, and then you change this one, 5, 2.5. Sorry, this is the importance factor 1. And this one is 5. So I included X, earthquake X and earthquake Y, and then I hit OK, and then you run your model, okay? Once you run your model, so right now I did everything. So my model right now is ready to get results, okay? So let's wrap up. You watch one video, you build the geometry of your model, and then you will define the window that we have for the response spectrum using the USGS values, and we put it copy paste, and then we define earthquake X, earthquake Y, and run the model. Once you run the model, you will end up having something like this. So let's see how we can get results from this model, how we can get the value of the base shear. So you guys have multiple models, right? Like around 10 models with different beam parameter, different spacing between something or so. So what I want you to get in terms of results for each model, this is very important. Number one, I want to know for each model, because we are doing a parametric study, I want to know what is the difference in the base shear. Number two, the shear lag. Number three, the maximum displacement. Number four, the inter-story drift. This 4 parameters. So at the end, you are gonna show me some curves. Relationship on the y-axis, the base shear, and on the x-axis, each model number 1, 2, 3, 4, 5. And then you will show me a graph something like this. Another one for the shear leg, and also you show me a graph like this, and this one and this one. So let's see how we can get results from here. Let's see the first thing, the mood shapes of the structures. So let me Actually, let me run the one that we just built and let it run for some time. It will take around 15 minutes or so, but I'm gonna work on the one that I already ran before. Oh man, it's closed. What is that? The horizontal axis is the model, like model number 1, 2, 3, based on the parameters that you have. Limits. New tab. Tabs. It's not this way. It sounds like it's still running. I'm trying to open one that I already ran before. Okay, sounds like this one is done. All right, let me show the 3D model. Okay, so this is how's the building look like. Let me show you how is the versed mood shape of this building look like. So what I'm gonna do, I'm gonna check deformate shape. When you go to deformate shape, it asks you if you want to show a case or a mode. So I want to show mood, and I want to see mood number 1. And let me hit apply. And it will take like a minute until the software shows you how's the mode shape look like. And if I start the animation to animate how this mood shape is look like, so I believe it's gonna be like an X direction. And it will tell you what is the fundamental period of the first mood shape. And if you look here, you'll find that it says it's a 6-second, 612, right? This is mood shape number 1. And I believe it's starting moving now. It wasn't a good idea to display the mood shape, but hopefully it's will be done soon. Yeah, so this is the first mood shape, how it's look like. It's an X direction. I'm not gonna show mode 1 and mode 2, sorry, mode 2 and mode 3 because it's gonna take a long time. But if we want to see a summary of the mood shape analysis and the fundamental period of each one, so you will go to display, show tables, and then in tables, you will go to structures output, and then I'm gonna uncheck this one, and you will find something is called modal information. And then you will hit OK. It will show you the summary of each mood shape, like what is the fundamental period of each mood shape, what is the participating mass. Oh, not this one. Display, show tables, it's the same one, but I need to check sub table. I need not all of them. So I want to see what is called modal participating mass ratio, just this one. And I'm gonna say okay. Yeah, let's see what we have here. I have 20 modes. I can run more modes, but let's see what is the characteristic of each mode. So it tells you mode 1 has period, fundamental period is, which is the fundamental period, 6.2 seconds, and it shapes 70% of the mass. So 70% of the mass is shaped by mode shape number 1. And then the second mode shape, you'll see, okay, so it shapes 70% of the mass, and all like the other ones doesn't shape, like Y and Z are zeros. If you get to Y, it's a 5.9 seconds, and it shakes at 71% of the mass. So this is the second mood shape, right? So what we are looking for a number of mood shapes that can shake more than 90% of the mass. We need a mass contributing or a mass shaking more than 90%. And the more that you increase beyond the 90, that means that your models are more accurate. Okay. So here you will find UX and you will find something called UX. So can you see mood shape number 1 is still 70, and after a while you can add much more mood shapes because mood shape number 4 is coming with 16%. And if you keep adding more shapes, I got to 94%. Like this is mood shape number 18. If you increase the mood shape to be 25, 30, 40, you can make this mass shaking like 100%. So what you can tell me like, okay, what if I just start by node number 1 and that's it? So that means that the weight effective that you have is 70%, not the 100%. Okay. But as soon as you increase the contributing mass in the nodes to 94%, so you are okay. Same thing with Y. If you go down, you'll find it's 94%. And same thing with the torsion. Like node number 3, can you see? There is no mass in X moving or Y, and all the masses is moving in the RZ, which is the rotation about, you see, 81%. So the third mode is torsion. Like the building is making like this. If I visualize it, you will see that the building is twisting. Okay. And after node number 18, you have 97% of the mass is moving. So this, if you want to see a summary of the loads. Next time, I'm gonna start the lecture with just like a few minutes talking about how to extract results for your report, how your report is gonna look like, what I want to see. I'm gonna show you reports from projects from last year, how it's look like, how to draw these curves, how to extract the base shear, how to extract the shear lag, and all these information. But don't think it's a very complicated. You just need to watch two videos. One video to build the geometry, and the other video of today, I'm gonna upload this one and the one from last year because I forgot to record how to input the seismic load. And then next time I'm gonna show you how to extract the results. So just the three lectures, you want to watch them and you will be done with the project, okay? All right, so see you guys next time. I uploaded a survey for this course. I put the link in the last announcement. So if you have some time, it's just like take 1 minute. Just your input, tell me what you general idea about what's going on so that we can enhance the course this for the rest of the year or even next year. All right, see you guys next time. Yeah, it's beam like the same column, 100 by 100, and you take it. Okay? Let me show you.
Like what I connect it to the outriggers.
Yeah, until it gets to the outriggers. But you know what? It doesn't have to like it doesn't have to go like this all the way to outrigger. Like it might. Let's assume this is your building, okay? You are gonna visualize the building in the XZ, and you have something like this. And let's assume the new outrigger is here. So when you do the bracing, it might get here. It doesn't have to reach to this point. It's better that you connect. It's better if you were able to. The thing is, the bracing need to connect columns, right? So if you were able to connect, let me tell you, you can adjust the outrigger rotation based on the bracing. Why? Because if you made the bracing is reaching the outrigger, it's a very stiff element here. That makes the bracing is working effectively. So you draw the bracing before the outrigger. And once the bracing is stopped at a specific location, you make it in the outrigger location.
But we have the outriggers set. Can we change it?
You already built the model?
No, I mean like the outriggers. And
Yeah, I told you to put it in a
It's set,
specific
right.
location, but I'm giving you like a permission if you want to change the location based on the bracing,
Okay.
because it's gonna make your model much better.
And as for like the diagonal for the bracing, like you would suggest what? Just connecting like column to column as it goes.
Yes, exactly. Yeah, so you will come here.
So when we draw it, it's drawn as column.
Yeah,
That's
like a column, yeah. So you will go for the easiest way to do it. You will go to view, set plane view, elevation view. Or actually you can do this like elevation. I don't know. Okay, let me make it at 0 G1, and let's make it at grids equals 0 and then apply. Okay, so you'll see something like this. Let me click F4 and okay, so you will zoom in here to this area, for example, and you start draw them one by one on the elevation until you
Should we use like I-beam?
you can use whatever cross section that you would like to. Even if you want to use the same column section, you can use it. So, and then you concrete, steel, whatever you want. So
Is it on all four sides?
Hmm?
It's on all four sides, no?
on the 4 sides, yeah. So what you are gonna do is you are gonna make like this, like it will go. Actually, it's gonna go up,
Yeah.
like this. And I give her permission if she wants, because it's better that you connect the bracing with the outrigger. Okay, you can change the outrigger location if you want. Like you can replicate it in the story that this bracing is stopped, because the much better for the bracing, it connects to the outrigger because it's gonna connect with a stiff element. So when it's gonna like you push the building, so the bracing is connected to a very stiff story.
And also the bracing should connect to the column and the Four sides.
Yeah, and the four sides. So here and the other side and the other
What
side.
if when we do it going upward, it doesn't connect to the corner of the top?
It doesn't have to be going to the corner of the top, so it
Okay.
can stop at any story. So, yeah, so just like you'll draw it like this, one by one.
Okay.
I'm not sure if you were able to draw them as a one beam that can.
Yeah,
You were able to do, so you don't have to do it one by one, so it's just like, if you calculate the ratio, like, this is.
Like 63.
It's
yeah.
45 degrees, so you can do it, once you do it one and you calculate how it's going, it's gonna connect to this automatically.
Okay.
So yeah, that's it.
Okay, thank you.
All right, so.
How about the coupling beams?
What about it?
Should we also make the increase in the stiffness?
Yeah, all the beams, all the beams, all the beams in your structure needs to be decreased in steps.
Quick question.
Hmm.
Do you recommend having two separate models for with seismic load added or something without?
Yeah, it's better like you have one clean one, so just in case if you messed up with the seismic load, so you can have a clean one to come back to.
Yeah, and we've only created the base model so far.
Okay.
So what I was thinking of doing is adding the